World Service last week, we cannot introduce it so much. Anyway, I wanted to first explain a bit about the title itself. I chose gravitational astronomy instead of gravitational wave astronomy because I think we do more than just gravitational wave astronomy. We will inform how gravitation works in extreme conditions. Secondly, I chose Einstein's name. Of course, it's centenary, but I wanted to look at gravitational waves and geometry in a way that's somewhat different in order to explain it to the lay audience or public outreach. So first I will briefly tell you what is one possible way of explaining gravity and relativity to general public using Newtonian ideas, just forces, including gravitational waves. And then the subject matter was supposed to be 4 different topics, but because I included this one, I cut out testing relativity. I've given talks earlier in the lab on testing relativity theory on that, so I just cut that out. So I will talk about EM follow-up of binaries before the actual merger actors, and how we might use gravitational waves to probe the geometry and dynamics of large-scale structure. And I end with a very exciting possibility of measuring the equation of state impacting fundamental physics. So without further ado, let's start with Einstein's equations, which relate the geometry on the left-hand side to matter on the right-hand side. The coupling constant that appears here, rather the inverse of that coupling constant, has dimensions of force. I would call this a geometric force or a fundamental force, and its value in Newton terms is 10 to the 44 newtons. In order to create any dent in the geometry, you have to apply, of course, stresses, not forces, and that will give you curvature. So stress is force upon area, and on the left-hand side you will have 1 over area, which is nothing but curvature. So you have to apply enormous stresses by human standards again in order to produce any dent in the curvature of space-time. So when can we achieve such enormous forces in nature? And so I started looking at this question and asked a very natural one that we would do, namely to take 2 binary black holes. So consider force acting on an orbiting body. We write it as mv squared by r, that's the centrifugal force, some would like to call it, but the more modern way is to call it centripetal itself. But according to Kepler's law, that 1 by r is nothing but v squared upon gm. So if you substitute for 1 by r, this quantity, then you can recast this whole expression, the force acting on a body, as v to the power of 4 divided by g. So again, going back to our fundamental force, then this is c to the power of 4 by g, v by c to the power of 4. You can see that this fundamental force, c to the power of 4 by g, does appear when we consider orbital force acting on an orbiting body, but it is suppressed by this large factor v by c to the power of 4. So typically v by c is of order 10 to the minus 4, even in a binary neutron star, typical radio binary pulsars. But in binary black holes, this v can approach c. Therefore, the force in an orbiting body can approach that fundamental force. If you don't have any black hole, then you cannot approach that speed v, and therefore you will never reach these very large forces. But what has that got to do with gravitational waves? I tried to put the strain produced by a gravitating object, in typically a binary system, that is the product of 2 binding energies, the internal binding energy, where R is the characteristic size, and is the characteristic mass of the body, and D is the distance to the source. So this is a simple formula that gives you the characteristic strain produced by a binary system, or in general by any gravitating object. And you can cast it as before in a way that you can involve the geometric force in the system of equations. So GF here is meant to be geometric force. So you can see that this same equation is Gm squared on R squared divided by R GF times R upon D, where this R upon D is just the ratio of the size of the body to the distance from which you are observing the body. This is the self force of the body, or this, the force on the surface of the body, the gravitating body, and that can be recast as before as V to the 4 by G divided by G. So what about, so here these factors we can become seen only in the limit that we have black holes, but the strain is further suppressed by R by D, and that R by D cannot be made to approach unity because typically the distance in which the wave is defined is greater than the at least one wavelength of gravitational waves, which is much, much larger than the distance, the size of the body, which means H is actually, even when you approach the wave, just very close to the object where the wave is defined, H is significantly smaller than 1. But you can approach that number. So this is the way I would kind of describe this in lay terms as to how gravitational waves can be produced, which are of order unity to the space-time geometry, and those enormous forces are available only in black holes. So this was my attempt to try and explain this to the general public. So let's leave that behind and look at the proper subject proper of this seminar. I'm going to start off with multi-messenger astrophysics with 2+ and 3G detectors, and also mention what might be possible with second generation detectors. I think in realistic terms this is probably going to be longer than just the second generation detector. So what is the problem at hand? Well, normally we talk about gravitational waves searches triggered by GRB, but we never talk about the opposite. Namely, searching for GRBs triggered by a gravitational wave. And this is not referring to the EM afterglows that will be observed after a gravitational wave trigger, but it's really referring to the prompt GRB emission followed by an emergence. So the question is, can we really accomplish such a follow-up by gravitational wave observations? No one knows really how promptly after the merge gamma rays are emitted. Hopefully, second generation detectors will be able to answer that question. If we have even a handful of events that are observed in coincidence with gamma ray bursts, we may be able to tell whether or not there is a delay. If there is a significant delay of the order of tens of seconds, hundreds of seconds, it would be extremely interesting to explore what is the reason for that. So I think that is the scientific case. But the question I'm really asking here is not so much the scientific case, but is there really a chance to do this, develop early warning, early enough, before the actual coalescence occurs, and do a swift follow-up? So let's first look at the fraction of events that can be observed in principle in coincidence with gravitational waves. So this is the maximum fraction of gravitational wave GRB coincidences you will be able to observe, assuming that you have an all-sky gravitational wave network and also an all-sky GRB detector. And that's plotted here as a function of the GRB half opening angle. The opening angle for a gamma ray burst is related to the jet that is emanating from the gamma ray burst source. And I take half opening angle to be between, of course, 0 and 90 degrees. In this case, it's completely isotropic, and here it is very finely collimated. The typical number for the half opening angle might be actually less than 10 degrees. Might not be the numbers that I have chosen, but for example, I have shown here, if the half opening angle is 20 degrees, then 20% of all events will be collimated towards us. And if the Hawke opening angle is 30 degrees, then nearly 40% of all GRBs will be collimated towards us. So if you assume that all binary neutron stars lead to gamma ray bursts, then that gives you an idea of what fraction of these events will be seen in our GRB GW coincidence, even if you have all kind of detectors. So what is the motivation then? So the goal is to observe as many GRBs as possible, aided by early warning triggers produced by gravitational researchers. So let's assume that the rate of binary neutron star mergers observed by detector is x per year. So GRB GW coincidences are likely to be about x by 50 per year. So where do I get this number from? Well, only about 20% of gravitational events will be potentially seen as GRBs, as I was mentioning. If you have half opening angle of 20 degrees, it's 20%. So about 20% of them will be seen. So that is this 20%. But a telescope like SWIFT observes an average 10% of the sky. That includes duty cycle and other considerations. In fact, SWIFT has about 20% strength of edge, but I'm taking the average duty cycle 10%. In that case, we have about 1 in 50 event observed in coincidence between GW and GRB. If you have a GRB satellites that can salute you in side direction, I will argue that we can improve this coincidence by a factor of 2 to 3. Not a lot, but still the underlying scientific motivation is that if you observe them, then before the particles leave, you can catch the physics that's associated with that. So that's the motivation. So do we really have an on-sky gravitational wave detector network? This shows here the antenna pattern for a gravitational wave detector network consisting of 3 detectors, the Hanford, Livingston, and the Virgo observatories. And their antenna pattern, all of them are working such that they cover the entire sky without any hole. They can observe gravitational waves from every portion of the sky. It's about something like 0.6, 0.7. It's the antenna pattern factor, even at the minimum. But if you have 5 detectors or more, then the entire sky has almost isotropic sensitivity. So a network of 5 or more detectors is always on and sensitive to most of the sky. The duty cycle of that is very low, that's true. But we can integrate and build signal to noise ratio coherently from all the different detector networks to increase the sensitivity. So those are the advantages, and in my study I have used 3 types of detectors: advanced detectors, a 3rd generation detector, and an Einstein telescope. The blue became pink here, but okay, to be able to produce figures beforehand, we should understand what the signal to noise ratio that is accumulated as a binary spiral develops. So what is plotted here is the accumulated signal to noise ratio in a single detector as a function of the time to coalescence or time to merger. So this is about 2 minutes before merger, that's the signal to noise ratio and so on. And what we see from here, for a source at 200 megaparsec, you can reach a signal to noise ratio of 6 in a single detector about 1 minute before merger. You don't need to be so stringent. You can bring this down to 5 as long as the total signal to noise ratio in a 4 detector network is 10 or more. But that gives you an idea of how the signal to noise ratio is developing as a function of time before merger. So you would reach something like signal to noise ratio of 6 1 minute before if the source is at 200 megaparsec. The same source, binary neutron stars, but now in LIGO blue, but placed at 500 megaparsec, would reach signal to noise ratio of 6 almost 2 minutes before merger. So that gives you a better chance. And this being a factor of 2.5, you can see I've increased the rate by a factor of 20. And still going further with Einstein telescope B, you can reach that level of signal to noise ratio of 6, 2 minutes before, but for source located at redshift of 0.4. The number of sources that you can follow up at such distances is pretty high, average about a minute. But it's not good enough to just have signal to noise ratio. You have good sky resolution to follow it up. So how well can you resolve sources from the sky? So this is the angular resolution 1 minute before merger using the same combination HI-LV network that I showed the antenna pattern at the beginning. The plot here shows angular resolution in thousands of square degrees. And what is interesting for us is really the part where it is less than 1/10 of the sky. So we're talking about something less than 4,000 square degrees. If that is less than 1/10 of the sky, something like a wide field GRP detector like SWIFT might be able to observe the source. And that's the idea. So you can see most, the entire sky has that kind of sky resolution. In fact, quite a bit of the sky has much better resolution than just 1,000 square degrees. But that is 60 seconds before merger. But if you then look at what's the sky resolution immediately after merger, then it's not 1,000 anymore. It will improve 1,000-fold, mostly coming from the timing information here, because you're seeing the high frequency part, it's few degrees. So as the observation takes, you can keep on improving online to pinpoint the telescope in the right direction. So that's what it is for a detector consisting of 4 detectors. So what would be the observing scenario? So the gravitational wave detectors produce a trigger 60 seconds before merger. A bat-like detector is glued to the sky patch predicted by this network within 30 seconds. Bat observes the prompt GRB engine and fixes the source within sub-second sky patch, and then you can assume you can follow up all other instruments to this method. The key is that you should be able to slew within 30 seconds, because in order to produce the gravitational wave events, you need to complete the analysis, therefore, within 10 to 30 seconds. So the challenges are that analysis should produce figures within few seconds after the signal reaches 30 Hz, taking that to be actually more than 20 seconds, not just few. Wall clock latency for data transfers, etc., is about 10 seconds. So analysis should be complete within 20 seconds. So that will give 30 seconds for the telescope to slew. I believe this is a sane number. It's not considered to be impossible. Telescopes are known to routinely do that. So if you then work backwards and ask how this early warning, what kind of sources can utilize that? Well, for advanced LIGO, the source has to be within 250 megaparsec, 650 megaparsec for LIGO blue, and Z 2.4, which means that, given these numbers, it means that 4% of all VNS events could be seen in GRB during merger, and this could be 2 even advanced LIGO, 20 in LIGO blue, and thousands. So that would be the conclusion for this. So I'll switch gear and talk about cosmology with gravitational wave observations. Here the motivation is to measure both the source luminosity distance as well as the redshift in order to map the universe. And the question is whether we can do both by gravitational wave observations alone. I'll first show you why this is would have been thought to be a fool's errand just about 3 or 4 years ago, but now there are at least half a dozen papers with really more work is being done as well. And the reason why people thought that this is impossible to do, namely to measure both the luminosity distance and redshift from gravitational wave observations alone, is because of a mass redshift degeneracy. We take a couple of minutes to explain what it is. So gravitational waves from binary black holes of different masses can all be mapped to one another. They're all similar in shape, identical in shape. And this is due to absence of any mass scaling in general. You can completely take out the mass from general total mass in general. So a binary of total mass m and z equal to 0 looks identical to the binary of total mass m into 1 plus z at redshift z. So this is the so-called mass redshift degeneracy, which means that you can't really infer both the total mass and the redshift, but only a combination. And this was thought to be the case also for binary neutron stars. This is definitely true for binary black holes where there is no electromagnetism present. If you look at general relativity and don't include any electromagnetism, vacuum solutions, right hand side of Einstein's equation is 0, you get nothing. You really don't have, you have to live with this mass redshift degeneracy. And for quite a long time, we thought that this would be the case also for neutrons. It turns out that it can be broken because of this fundamental idea, or basic idea. But binary neutron star spiral is followed by a merger waveform, which is unlike the binary black hole case. It is preceded, the final black hole formation is preceded by a merger waveform, which is characteristic of the material. So the merger signal really depends on the equation of state of the system. For most equations of state, heavier neutron stars are smaller, unlike black holes. If you make black holes heavier, they become bigger. But for most equations of state, in the regime we are talking about, if you make the neutron star heavier, it will become smaller. But heavier neutron stars means that the post-merger oscillations will be at higher frequencies. Because it's smaller, the frequencies are higher. But here is the tension. The tension is that cosmological expansion causes the frequency to redshift, which makes the observed mass of the binary larger, but larger mass means greater frequencies. So these two effects that I'm talking about are actually in tension, and that's the reason why it's possible to do cosmology with the help of microphysics. So let's look at that in terms of equations. If you look at the post-Newtonian phasing formula, it has mass and frequency appearing together as a product. So you have this phasing of gravitational waves, that's written, mass and frequency appear together. So if F is transformed to F upon 1 plus Z because it's the source is at a certain redshift, you can change n to n into 1 plus Z, and you have exactly the same equation as before. You can't have the difference. Okay? Of course, there is also the amplitude term, but we don't determine things by amplitude. It's only by the frequency development phasing. The tidal term, on the other hand, cannot be scaled like that. If you look at the tidal term, then it has the usual post-Newtonian phi mf to the power of minus 10 by 3. Actually, it should be plus. It's all, I already put it in the denominator, so it should be phi mf to the power of plus 10 by 3. And then m and f appear together here, but m and this r is the size of the neutron star, they appear separately. So if you try to rescale m here, that will be affected. So this is the basic principle that we deploy in measuring the neutron star, using binary neutron star, even neutron star black holes, the redshift of the source. Of course, this is a high post-Newtonian order term. It's already the 5th post-Newtonian order. And so the effect can be, is most of the time small, except when this the two objects are very close together because this factor here is typically all the time large. As a result, when the two black holes, neutron stars are close, you can really have that kind of effect large and measure it. This is a schematic way of understanding what it is. Namely, the inspiral part of the waveform allows you to, gravitational mass as a function of redshift. This is the degeneracy I'm talking about between M and Z. That's the degeneracy. But you break that because you have mass, intrinsic mass of the binary that can be measured something like that, intrinsic mass of the two neutron stars that can be measured. So in reality, how well can we do that? But it depends on what is the effect of cosmological redshift and the different masses. As we make the masses heavier, how will the spectrum change? So here is our spectrum of the signal as a function of frequency, only for the merger part of the signal. What you see, of course, is when you shift the signal from z equal to 0 to 0.5, 0.5, 0.1, 0.15, the spectrum shifts to the left. That's the redshift that we know very well. But if you look at what is the effect of the mass, if you make the mass higher and higher by the proportion that we are talking about previously, you can't quite see in this graph, the effect is there. You can see from blue to, the spectrum has moved from blue to that magenta color. So it has moved a little bit, but it's a log scale, it's higher frequency, so the effect is not negligible. So there are typically two, so this is the inspiral part. This was a short simulation, by the way. That's the reason why you don't see the full inspiral part of the signal here. This is the inspiral part, and then that's the merger. And there are typically two frequencies here. These two frequencies are what one is trying to do, F1 and F2, is what I would call it. So what we did was to take a bunch of numerical simulations, change the masses, even very slightly, going from 2.68 solar mass neutron star binary to 2.97. But that gives you a significant shift in both F1 and F2. So the spectrum that we see is those two peaks, and we fit a model to that and use that model in seeing how well we can measure the equation of the redshift. So there is a fit between the frequency of gravitational waves and the mass. Those are the two frequencies, F1 and F2, and they depend on the mass in this particular. So how well can we measure the neutron star redshift? How far it is? This plot shows you the accuracy with which we can measure. It's a plot similar to the schematic that I showed, mass on the y-axis and redshift on the x-axis for 4 different cases that we consider. And it turns out that you can measure the redshift as an intersection. Each by itself would be completely hopeless, but if you take the intersection of those two, because they're working in opposite directions, you can measure the redshift typically to about 10% or so. So completely just from gravitational wave observations, up to redshift of about 0.05, you can measure to within 10%. It will degrade, of course, if you go to higher redshift. Hope is to use this in order to get some idea of what the redshift is, even within 10 to 20 or 50%, even at redshift of something like 0.5, which is the reach of the challenge here would be that we need to have good waveform models of the merger epoch. I'm showing the results for purely the merger epoch. We can also use the inspiral phase in order to estimate the redshift, and that would be useful to combine both the inspiral and merger. That would be a nice research problem. But in addition to knowing the waveform models, it's also important to know what's the neutron star equation of state. I was assuming in those previous slides that I know what the equation of state is, And the hope is that by the time we have these 2+ and 3G detectors, we will measure the neutron star equation state. So what's the prospect of measuring the neutron star equation state accurately? That's what I'll talk about in the next 10 or 15 minutes that I expect. Measuring the neutron star equation of state is of fundamental importance because we really don't even know what is at the heart of what we call neutron stars. They may not even be neutron stars. We can use the merger dynamics as before, but the merger dynamics now has to deal with the tidal interaction between the neutron stars, and they are present both during the long inspiral as well as during the merger phase. What I did in the study that I showed you before is to use the merger dynamics to estimate the redshift. But in the remainder of the talk, I'm going to use just the inspiral dynamics to see how well can we measure the equation of state of neutron stars. There are hundreds of equations of state, and they're all characterized by what is the dependence of mass as a function of radius. And most of the equations of state to the right of this figure are still not ruled out by accurate measurements of masses in radiobinary pulsars. So this is the heaviest known neutron star, and its mass, very close to 2 solar masses, still does not exclude most of the equations of state. And a single accurate measurement of neutron star radius within about 1 or 2 kilometers can actually rule out many of the models. If you combine the accurate mass measurement and also radius. Of course, it's not the same system, and the goal is to be able to do that for the same system in order to extract the neutron star equation state. So let's look at what is at stake. So there are all these different equations, and neutron star radius can in principle be measured by X-ray observations, but they do have a lot of systematics. And talking to some of the astronomers, I believe the neutron star radius might not actually be determined accurately to within even 10 kilometers. It might be anywhere between 8 and 18 or 20 kilometers. That's the radius of neutron stars. Gravitational wave observations could in principle provide a clean measurement of neutron star equation state. So how do we do this? Well, several authors have suggested by now to use post-Newtonian tidal effects to measure the equation state of neutron stars. There is this long list of authors that I'm giving here, and the basic idea is the following. And I've already talked about neutron star tidal effects, namely the tides that are created on one of the neutron stars due to the other neutron star will affect the orbital dynamics. And the way it affects orbital dynamics is dictated by a parameter called lambda, which is the size of the deformation that is produced in the neutron star due to the tidal field of the external source. In this case, the external source is the second neutron star itself. So this lambda is related to the size of the neutron star. Goes by the 5th power of the size of the neutron star. And most of the people, the real interest is to measure that lambda, how big is the lambda. And instead of using this small lambda, most people use this capital lambda, which is a dimensionless number. So this has dimensions of r to the power of 5 in, you have to, well, it really doesn't have dimensions of r to the 5. It is kilogram, meter square, second square, but I'll put this in C equal to G equal to 1 case. You have to multiply it by certain factors and mass the neutron star and can make it dimensionless, and that parameter is called the tidal deformability parameter. You can call this also tidal deformability, and its value is between about 300 and 600. For small variations in neutron star masses, and also for different equations of state. So that's the range over which this parameter lambda changes. It could be even larger depending on what equation of state you take. So where is the signature of neutron star equation of state present? Well, it is present in different places. It's different. It's present in the inspirer phase. It's present in the merger phase. But the current estimates are really not using the merger phase. They are using only the inspirer phase. It would be really nice to see to combine these two. So in the context of the different detectors, a signal at I believe this was 100 megaparsec. That's how the signal will look like. And so it is above the noise curve of advanced detectors. So how well can we measure? And this is a recent work by Del Pozo et al. That takes into consideration all the events seen by advanced detectors during its operation, and then combines them one by one instead of looking at events separately, which is what most of the previous work did. They actually combine the results, and by combining, you see what happens is this lambda naught, which characterizes this type of deformability, for three different equations of state, as given by the dashed line here. From there, at the center here is the true value. That's the true value there, and the true value for the red one is here, and likewise for green. So with about 20 events before that, it's hard to distinguish between the different equations of state. But by the time you have about 25, 30 or 40 events, you begin to really completely separate them out. I would say somewhere here is the point when you have it. This is for some extreme equations of state, that's true. The chosen values are such that you have either very stiff equations of state or very soft equations of state, but that's what we do with these operations.
When you say group events, do you have to put a mass cut that they ought to get similar masses, or can you just take any events that come our way?
Any event that can be confirmed to be binary neutron star can be chosen. It doesn't have to be mass ratio is only.
This must be a similar.
No, what they did was to simulate what happens in advanced light. Throw events randomly.
It's a distribution.
Yeah. In fact, you might as well argue, you might like to argue that, oh, maybe there's only one event which actually influences the whole thing. But I think if you look at the way the whole statistics is processing, I think it's, every event seems to have an influence. In some of the other works, it looks like, one or two events seem to make a lot of difference. That is true. But I think here you can see the correction here is making some difference. What are the challenges here? We need faithful waveform model. That seems to be the biggest challenge in constructing or inferring the neutron star equations. What do we mean by that here? The faithfulness is not to do with the vacuum solutions, which I will mention in a minute. It is to include matter, namely other forces of nature, not just geometry. Rotation may have influence. In fact, we know that neutron stars can have significant spins, and that spins can affect the dynamics. Therefore, it is important that neutron star merger simulations include appreciable amount of spin, something like 0.2, 0.4 in dimensional spin number. Magnetic fields are probably not important, but including them and showing and quantifying what is the extent of that effect is important too. There could be others, but these are the ones that I think are the most important. Okay, so how well do we really know the waveform and what are the challenges? Vacuum solution, which is binary black holes, that's what I mean, is known pretty well. And inspirer phase is mostly dominated by terms that are due to this vacuum solution, up to 5 p. And if they can be captured properly, then at least one part of the problem is solved. And there is good agreement between numerical relativity simulations and over hundreds of cycles from some recent work, which is as yet unpublished, that shows that. But I think it's still necessary to confirm that there is no dephasing between the model and the reality of all the 1,000 cycles, maybe a couple of thousands. Numerical simulations with matter is still at infancy, I hope to be clear. BNS merger simulations don't converge really well. Comparison between different groups is necessary, and longer BNS simulations, where we can rely on, let's say, binary black holes plus tidal terms added by hand, but to confirm that that works over the last hundreds of cycles is still necessary. This is what we needed, but I nevertheless don't think that we need to be too scared. And this particular work by Wade et al. And also other people, trying to make the point that our waveforms are everywhere, and we really don't have a clue. And I really take issue with that, because the point of this was to estimate what is that lambda tilde parameter by using your template as one particular family, but doing injections from other post-Newtonian families that we have. There are many post-Newtonian families. In fact, when we wrote the code for binary black hole extraction, I counted, there are something like 45. Why stop here? We can include all those 45 different things. I think they were done initially in the 90s in order to better understand the post-Newtonian dynamics, its convergence and things like that. That work precisely led to the development of better models. And I think we now know the waveforms better than the flexibility allowed by the post-Newtonian equations. So I do not think that the real situation is as bad as this. I think we already need to be better. I'm not trying to say that we don't need progress. We need progress along the lines that I mentioned, but it's not as bad. And let me just finish by showing this spectacular plot of comparing effective on-body numerical relativity simulation, both for non-spinning binary black holes and spinning binary black holes, over tens of cycles, and there's about 60 cycles or so. But more recent work actually has even better, even larger number of cycles, and here I believe the agreement is limited by numerical relativity. So the future looks bright, but there are many challenges. With that, let us stop, and thank you for your attention.
Other questions for the speaker?
So, Sathya, very nice talk. Thank you so much. I was impressed by, I was curious about your analysis with the Swift follow, with the claim that Swift could be pointed before the actual merger. What I didn't understand about your numbers is you mentioned that the Swift bat sees something like 10 or maybe 15% of the sky. But of course there are other GRB monitors like Fermi GBM that see something like half or 60% of the sky. Yeah.
I think we need a Swift-like instrument because we can't just stop at identifying the GRB. There's no screwing needed there. They don't even need an early warning system anyway. I'm talking specifically about instruments that have not only wide field coverage, but also they can pinpoint the source once they have identified within arc minutes, few arc minutes, so that they can be followed up further. I think I may not have set the motivation. The motivation is that there are plenty of different models that talk about immediately after following GRB, long X-ray, long after order of hundreds of seconds. And those things have not been observed. In order to do that, you need to identify the source promptly and then follow it up. Yes.
Any more questions? In that case, before we thank your speech again, let me remind you we have another very exciting seminar coming up next week, so mark the date, and there will be snacks and drinks outside. So thank you very much, and thank you.